In this video, we're talking about the subject of symbol synchronization, and that's the term that I usually use, but I noticed in the book he calls it timing recovery, and sometimes you'll see, if you're reading a book on digital communications, you might see something like baud synchronization or baud recovery. Baud, B-A-U-D, that's another artifact from the past that sometimes people use. Okay, so what I want to do in the video here is review the problem. I know we're doing some somewhat complicated things and it's easy to get lost in the details, so I want to make sure you understand the problem we're trying to solve, so we'll talk about that a little bit. Then we'll talk about a cost function that we can use in our optimization technique to solve the problem. And we're going to, of course, minimize a cost function just like we've done with several other problems in this course. All right, then once we have the cost function, we can derive the algorithm. I can run through some of the MATLAB code that would implement this algorithm, and then we'll run some examples. All right, so that's the plan. All right, and so let's get started. All right, so I've drawn a waveform here, and I've used my favorite shape for drawing pictures, which is the triangle waveform. In our examples that we're going to use for the rest of the class, we're going to be using mainly square root raised cosine pulses. And of course, those are much harder to draw. So these are proxies for raised cosine pulses, all right, or square root raised cosine pulses. So it's just illustrating the idea. You're not going to get triangle waves very often in the problem sets from now on. Okay, so to get started here, let's first of all remind ourselves of the what we've been calling the upsample factor m. Okay, so in this particular drawing, m is equal to 6 if the grid lines are the samples. All right, so m comes from the definition of number of samples in a given symbol, and so far we've restricted this to be exactly integers. All right, but in practice, you don't necessarily have to have the number of samples to be, number of samples in a symbol interval to be an integer. All right, so I've drawn this with a lowercase m instead of an uppercase m. That's to try to help remind you that it doesn't have to be an integer. Okay, so we'll see, because we're starting to do some interpolation, we'll see that we can get away from the requirement that the upsample factor be an integer. All right, but in this picture, I've drawn it with an integer. M is equal to 6. Okay, so the problem we're trying to solve here is that, let's say we have a received waveform. Okay, and of course, in practice, it'd be samples of the received waveform. But let's say we have this. Okay, and this lines up on the time axis like so. We would want to start downsampling this waveform at sample values 4 for the 3 pulse, 10 for the pulse that has a peak of 1, okay, 16 for the -3 pulse, and you get the idea. Okay, so we know that the sample values are 6 units apart, so the first peak occurs at 4, and the next peak is 4 plus 6 is 10, and so forth. So we get that idea. The question is, could we automatically detect that? So if the waveform looked like this, we would start sampling at 5, 5 plus 6 is 11, so the next sample would be 11, and so forth and so on. And then we also talked about, well, what if it lines up halfway between samples? Wouldn't it be better if we could start sampling at 4.5? Okay, and we can do that with some interpolation. Okay, so we're coming up with an algorithm that will automatically determine where the optimal downsampling time is. So timing recovery, timing synchronization, symbol synchronization, all these are words for what we're trying to do. Okay, so make sure you understand that concept, and we'll move on from there. Okay, so as far as the reading in the book, I was looking at it, and what I would recommend is that you read this chapter. Timing Recovery is the title of the chapter, But there's some examples that I think add a little more confusion and take a lot of mental effort for what I would think to be a limited payoff. Okay, so I want you to skip the section called An Example, and then we're also just going to look at one particular cost function. There's lots of cost functions that you could use, but the whole idea of this course is to give you a survey of ideas, and so we're not going to spend a lot of time looking at different algorithms. So let's skip output power maximization, and we're going to get to the idea of real world constraints like the channel effects. We're going to get that a little later, so let's postpone the discussion of the 2 examples section from the book as well. Okay, so that cuts out quite a bit, and quite a bit of the stuff that's actually mentally challenging to sort your way through. So read that, read the remaining parts, the parts that I don't mention skipping. Okay, so from here, what I want to talk about first is this idea of a cost function, and this cost function is going to be called, or I call it, decision-directed symbol synchronization. Okay, he uses CV, that stands for cluster variance. All right, and he motivates that title from, a previous section that I told you to skip. So don't worry that that's a CV. The fact that it's decision-directed is what I'm most interested in. Okay, and so when I say it's decision-directed, what I'm talking about here is that we know that we downsample, and then we also know we're expecting our symbol values to be 3, 1, -1, or -3. Okay, so we can plug into a quantizer. All right, so I take a possible symbol value, x of k. All right, I'm downsampling at a certain time, x of k. I plug that into the quantizer, and it's going to give me an answer. Okay, if x of k happened to be, let me mark this down, if it happened to be a 3, okay, x of k 3, you put it into the quantizer, it's going to quantize as a 3. That would give you 0 error. Okay, so that would be good. All right, let's say we had a quantized value of 2.5. I'm sorry, downsampled value of 2.5. 2.5 is going to quantize to 3, and that's going to generate some error. So the further off this is, the more error I'm going to get. Remember, you parentheses and square it. Okay, so we're adding up any differences between the downsample value and the quantized value. Now I give this example for x of k close to 3. The same thing would apply for any of the other symbol values. Okay, so we're taking a look at this cost function and what happens on average. Okay, so you see the averaging step here when you take a look at this squared difference. Okay, so I don't think that's that hard to comprehend what we're doing. We're quantizing a particular symbol value. If it's way off, it's going to generate a bigger error. And we're trying to minimize that error by choice of downsampling times. Okay, so I do think what's a little intimidating when you look at this is that we see things like x of k. What the heck does that mean? Okay, and so you have to remind yourself this is really a shorthand. Okay, so x of k is really coming from x being the received signal. All right, and then the common notation is if you use curved brackets, we're now talking about the analog signal domain. Okay, so we take a symbol sample. Okay, the symbol sample should line up at kt over m, right? Every m samples, we should get a symbol, but we realize we might be off by some fraction of a symbol. Okay, so in those pictures that I drew before, I said, okay, it looks like we might start downsampling at 4. If it lined up exactly with 4, and then tau would be 0. Okay, and then I moved it over, and I said, by that I mean kt over m is equal to 4. Okay, and then I moved it over a little bit and said, what if it was like this? if this was kt over m is equal to 5, then tau would still be 0. But what if it were halfway in between? Okay, so kt over m could be 4, and then tau would be 0.5, and our optimal downsampling time would be at sample 4.5, even though we know the reason we're getting these fractional samples is because we're doing some interpolation. Okay, so quick summary: x is the received signal. We're downsampling at certain times, and we're trying to figure out what value of tau would give us the best in terms of the cluster variance to give us a decision-directed symbol synchronization algorithm. Okay, so that's the goal. I'm going to clean some of this up. And so next, we know what to do. We've done this many times. We're going to update tau. So we take the old tau and we look at the derivative of the cluster variance evaluated at the old tau. All right, so we update the new tau based on this equation. All right, so from here, it's just applying some of the math. All right, so we take this derivative with respect to tau, okay, so d tau, and we push it inside the average. All right, so I have this derivative showing up inside the average. All right, I apply the chain rule, okay, and with the chain rule, I have a couple of assumptions. All right, so first of all, this 2 comes down to here. All right, then I copy the outer bracket. Okay, so that goes here. All right, and then I multiply by the inside derivative. So the inside derivative is dq d tau, but you know they don't say this in the book, but once you quantize, you know, quantizer looks flat at small steps away from tau. So dq d tau should be 0, okay? So we'll make that assumption, dq d tau is 0. And then I'm left with derivative of x of k with respect to tau. All right, and that's got a minus sign on it here, so that's where this minus sign comes from, and then this is the inside derivative. All right, so that's essentially the math. It's not that complicated. It's just that how are we going to get this? This is from samples. Well, remember I had a whole video that talked about how you could make an approximation of the derivative of sampled data. Okay, so this is where that comes from. All right, this is in one of our videos, so you can look at estimating a derivative from sampled data. And so all we do is we use this interpolation routine to plug in these values into the sync interpolator, plus delta and minus delta, and we take that subtraction and we get something that's proportional to the derivative. Okay, so in practice you might notice you divide by 2 delta to get the actual estimate of the derivative, but we can absorb that into this mu constant. And so I drop the delta out of the math here. All right, so that's the math. All right, so think about that. I know that some of you really love the math, so you can dive into that. So at this point, I'd like to go over the MATLAB code that implements this decision-directed symbol synchronization algorithm. All right, so what I want you to do is think of the variable t now as the current downsample time. Okay, so for example, way up here, when I started, you know, you're going to start with downsample time of 4. All right, if you happen to not need an offset tau, the algorithm will immediately converge, but you would start at some downsample time, and we're going to go in steps of m for t now, so that we choose the proper downsample intervals. Okay, so you'll see that when we go through the code. Tau is the variable that we're using to represent the sampling offset. Remember, we could have fractions of a sample here coming out of this algorithm. All right, in the book, he uses lowercase l in the algorithms, and many times he also, or at least I do, I use uppercase L to represent the number of symbols in the square root raised cosine pulse function. Remember, when we look at the number of symbols, it's the number of symbol intervals in front of and in back of the current symbol interval when you use the square root raised cosine pulse. It turns out that most of the time L can equal cap L when you run these algorithms. It really doesn't matter. But I've played around with a few examples where if you increase lowercase l is used for interpolation, and for a fixed uppercase L where you are looking at the number of symbols, sometimes the algorithm runs better with a larger value of lowercase l. All right, so I just want to point out that, lowercase l, which by the way looks like a 1 in MATLAB, so you need to look carefully, but this shows up here whenever you do the sync interpolation step, or what he calls interp sync. Okay. Let's see what else to tell you. All right, so T now, that tells you the starting time. Now remember, when you initialize this, if you're using square root raised cosine pulses, there's a delay between when you get the peak from the pulse, okay, and from when you initiated the pulse. All right, so let's say we initiate this at time 0. It's going to take L times m plus 1 samples before the peak shows up. So that would mean that the downsampling time should start at L times m plus 1. All right, so in this case, this should be a capital L, all right, because we're talking about the number of symbols in the SRRC function, all right. I'm going to draw a quick sketch to make sure you understand what I'm talking about. Okay, so SRRC looks like this, all right, so you have L sample periods in front and in behind. Okay, so you have to go L times m before you hit the first valid T now value. Okay, so if that's confusing, don't worry about it. Just know that T now has to start somewhere. All right. So from here, the algorithm is just setting up some variables. All right, one of the most important variables is XS, okay, because this is going to be the variable that we're storing the symbol values, right? We're trying to convert this waveform into just a sequence of symbols. So XS, S for symbols, is going to store that. All right, we have some initialization parameters. We're keeping track of the tau values so that we can plot them. We have a convergence parameter. We have a delta parameter that's used for the derivatives, to estimate the derivatives. And then what goes on next is we simply start a while loop. All right, this could have been a for loop, all right, but he chose to use a while loop. And so we're looking at T now, the sampling time, the current sampling time, okay? And while you still have some signal, and you can't go too far, you have to stop at some point because you don't have enough data at the back end of things. All right, so that's why he subtracts that 2 times L times m. All right, if you just used length of x, you'd throw an error. All right, so as you go through the sampling loop, you increment the index counter. All right, and you start keeping track of the symbols. All right, so we're going to use the interp sync function to look at the received signal. All right, so remember x is this vector of received signals. We are downsampling at T now plus tau. Tau is initially 0. And we're using the interpolation over L symbols. Okay, I'm sorry, L of the sync functions from the previous video where we talked about interpolation. All right, the next step here is we calculate, we add a delta and we subtract a delta so that we can come up with an estimate of the derivative. All right. From there, we quantize the downsample value. All right, so that gives you XQ. And then you simply implement the update equation. All right. From there, you update T now to go to the next symbol interval, right? We know that these symbols are supposed to be M spaces apart, M samples apart. Okay, M doesn't have to be an integer with this approach, and so that's part of the power of it. In the examples that we start with, we're going to make M an integer, but it doesn't have to be. I want you to know that. So you update T now, and then you go back to the top and you start over. All right, every time tau gets adjusted, and so it should keep track of the optimal sampling time. All right, so tau can actually drift up to be more than 1. I talk about it being a fractional sample, but if you're off a little bit and you need to move a whole sample value over, tau can take that into account. All right, so I'll run some MATLAB examples and show you this code in action. Okay, here's some examples of running the symbol synchronization algorithm in MATLAB. All right, so let me walk through this code. So first of all, I found some cool commands to set the size of a figure automatically whenever you run, so I'm not constantly having to resize the figure. So I thought that'd be a good tip to pass along to you. All right, so in this code, we're going to generate random PAM sequence in the usual way, and then I'm going to modify how I create the transmitted signal a little bit. I'm going to go into more detail on this in a different video, but this modification allows us to do a more general modeling of how I send symbols. I won't have to send them with some integer upsample rate. Okay, so we'll talk more about that in a different video, but the way this starts here is I can just give it the sampling rate of the system, and I also can give it the symbol rate. So if you take the ratio of these turn out to be an integer value in this case. So later on we'll move away from that, but I just wanted to set that up for you. The most important parameter that we're going to play around with this video is the offset. Okay, so we're going to have these. We're going to transmit these square root raised cosine pulses every m samples, okay? But there's going to be an offset, and the offset can be a value that has a fraction with it. So maybe it's offset by 1.5 samples or 0.5 samples or even minus 1.5 samples. We can play around with this parameter and watch the algorithm operate under different conditions. Okay, so again, this first section is simply just making the transmitted signal and then receive filtering it. So we're going to start here, assuming we have, demodulated the signal, we back down to baseband. This is the received signal. We're trying to then downsample it at the right times. Okay, so this code is pasted from the TB MATLAB book or the TB MATLAB file section. However, I made some modifications. I modified it to be a dual loop. I wanted to show you, a more general case in a different video. So I made this dual loop. Initially, we're going to turn off the second loop, but I wanted to have that for you. We need to know this ideal upsample factor. Okay, so that would be f sample over f sim. We know that value a priori. We could have it where the symbol transmit rate is not exactly what we're expecting, and so later on we can modify that code, but for now we assume we know that exactly. Okay, it's very much like when we had a carrier frequency and we said maybe there's just a phase offset, and then later on we used that algorithm to actually incorporate an adaptive technique for accounting for a frequency offset, not just a phase offset. Okay,
So in a previous section of the video, we talked about L is the value used for interpolation. We've talked about interpolation quite a bit with different videos. All right. So next we have some initial tau estimates. I think it makes sense to start at 0 there. N is the total length of the PAM sequence, and mu1 and mu2 are the convergence factors. All right. So I wanted to turn off the second loop, just work with a single loop symbol synchronization technique for now. And we have a mu value that we can play around with, and we'll see this thing in action. All right, so you have to start with an initial t-now. T-now is the downsampling value. You want to get that reasonably close, or it takes a while for the eye to open, which is not necessarily a bad thing when we're first looking at things. But in general, if you're writing an algorithm, you'd like to have the algorithm start to work sooner rather than later. Okay. The algorithm was written with x as the received variable, so rather than change all instances, I just put x equal to yf, where yf is the signal that I made. All right. Delta is the step size that we use to estimate derivatives. Okay, you don't need a real tiny one, because the goal of the delta is to simply get you in the right direction when you do your adaptive algorithm. Okay. Now, as we've discussed, XS is the downsampled values, right? These are the symbols. So the symbols are going to be stored in XS. So I am making an array that's initialized to 0 for that. And we're going to keep track of our tau estimates. So that's what these next two lines do. Okay, so we've already gone over this a little bit, but t-now, we're going to update t-now every time through the loop. We have to stop before you get to the end of the X sequence. I stop relatively conservatively so I don't have to, keep running out of array space in MATLAB. So I did 10 times L times M. You can actually get by with something smaller for these examples that we're working on, but it's just a stopping time. Don't sweat that detail. Okay, so as we go through the loop, we're going to increment a counter so that we can store the downsampled values in the next index location for the array XS. All right. Let's skip down. We're going to turn off one of the loops. All right. So what's important is we store XS into an index location. We use interp sync at t-now plus tau1 plus tau2. Tau2 is turned off. Okay. We estimate the derivative with these 3 lines of code. We quantize and form our update equation for essentially tau1 and tau2. Okay, so I turned off the tau2 loop. You can turn off the tau1 loop. Either way, it works. Okay, so at the end, we update the new time variable in consideration. We know these theoretically should be spaced apart by m. In these examples, they are exactly spaced apart by m, the way we designed this, but there could be a little bit of offset that gets taken care of with the dual loop. All right, so that'll be a different video. Okay, so that gives you an idea of the code. I know it seems like a lot of details, but remember, it's just the math that we developed earlier in this video. Okay, so let's see it in action. All right, so I'm going to start with an offset of minus 0.5. Okay, I'm running 10,000 symbols so that you can see what happens with XS. So down here at the end, I'm going to plot the XS values, the sample values, and it's going to look like a soft decision diagram. So let me run that. Okay, so you see it runs reasonably fast. I put a, it's going to be interesting what the update, the mu value can give you here with these eye diagrams. But you can see initially the eye is sort of, it's open. You wouldn't be making errors here, but eventually it tightens it up because we're getting more and more of a correct downsample time. So we start with an offset of 0, and we counter that with, let's see, what did I put for the offset time? I put an offset time of minus 0.5. All right, and you so you see the algorithm, back when I get to the graph here, is counteracting that offset of minus 0.5 with a plus 0.5 correction. Okay, so it cancels and gets this tightened up. So you can see once you get to this region of the offset graph, the eye diagram is pretty tight. Okay. Another example I wanted to show you. Look what happens when you put the convergence factor to be something really small. Okay, so when I run that, it gives you a cool looking plot where it's maybe that's too small. Okay, so let's do 0.01. Okay, so when you run that, it gives you an eye diagram where, yeah, the eye is still open, but it's taking a while to tighten up. All right, another interesting case. Let's say we make this offset minus 1.5 samples. Okay, so in that case, when we run this, wow, the eye's not even open initially. Okay, so it takes a while, but it's converging, and eventually the eye opens, and we're getting correct downsampling times because we see our symbol values. Read these across. That's close to 3, close to 2, close to 1, close to minus 1, close to minus 3. All right. You can see it's eventually correcting for that minus 1.5 with a counteracting plus 1.5 value for tau. Okay. Another thing I wanted to let you know about is this algorithm seems to be pretty robust to the update parameter size. So if I make that 0.1 and rerun it, it converges pretty fast. Okay, opens the eye, tightens it up pretty good, and that would be better than the previous value of mu. So you keep pushing that. Let's get this all the way up to 1. Does it break things? And so when you run it, you don't even get a little bit of a blur. It really quickly goes to the right algorithm. You see it at the right value. It has a little bit of jitter, but it's quickly opening the eye, and it seems to be working fine with even a relatively large value of mu. Okay, so it doesn't seem that this algorithm is particularly sensitive to mu for this particular example. We get a little more interesting plots if we make mu a smaller value, because it takes a while for the eye to open, and it gives us some information about how things are working. But of course, practically, you'd want the eye to open as fast as you could. All right, so there's a simple example where you just have a known offset, and the symbol rate at the transmitter is exactly the same as the symbol rate at the receiver. Okay, so in the next example, which will be in a different video, we're going to take a look at what happens if the symbol rate at the transmitter is a little bit off from the nominal. Okay, we're expecting a certain symbol rate, and we're off by, say, 1%. Can this algorithm work with that? And obviously it will, or wouldn't have brought it up. Okay, all right, so there you go. Hopefully you understand what's going on with this. Give me some feedback if you feel like you're lost, and we can figure out a way to talk about it.